Okay, Chapter 3, Section 6, Derivatives of Logarithmic Functions. Okay, so here's a nice graphic to remind us of the graphs of logs in general. Remember that the domain of any log function is going to be equal to all real numbers, positive numbers. So domain is any value that's strictly greater than 0. So from 0 to infinity, not including 0. And the range is all real numbers from negative infinity to positive infinity. Okay. Remember that if we had a function y equals to e to the x power, then we can apply an ln to both sides. So y equals to e to the x, and then we can apply the left-hand side as an argument of the ln function, the right-hand side as an argument of the ln function. And of course, the right-hand side just reduces down to x. So we get ln of y equals to x. So that becomes our new function. And remember that in this case, this would be a new function where this becomes the input and this becomes the output. And of course, in algebra, we love to put the x as the input. So we just flip it around and say that the inverse function is y equals to ln of x. So these are inverse functions. Right? Where x always represents the input of the function and y the output. And then in more general, if we had y equals to b to the x power like this, then again we can apply an ln function to both sides. So ln, we can apply a log. So let's do it log base b. Similar to above, we can apply a log base b on the left-hand side, y equals to log base b on the right-hand side, e to the x. On the right-hand side, these two collapse to just become x. And so again, we get the same kind of thing, log base b of y equals to x. And again, we have an input-output relationship. Right? If we think of this as our new function, then in this function, this becomes my input to this function. Input this value into this log base b, and the output would become this x. But algebra loves x to be our input variable, so we can just switch those around. And then we could say that y equals to log base b of x is the inverse function to this one. Okay, so just reminding you a little bit about logs and exponential functions. Keep in mind that in this case, then this is also for b. This is good for b being a member of the set between 0 and 1, or from 1 to infinity. So not allowed to be 0, not allowed to be 1, any positive number. Okay, so now in this section, what we're interested in is figuring out the derivative of this. What is that? So derivative with respect to x of log base b of x. That's what we're interested in figuring out in this section. Okay, so let's get to it. Given y equals to log base b of x, where, of course, b is a member of the set between 0 and 1, union 1 to infinity, somewhere in there, so it's a valid argument of our log function. Then, and of course, well, x has to be in the domain of log base b, which means it's got to be a positive number as well. Okay, so given this, let's find y prime. Find y prime, right? We want to find the derivative. Okay, so let's go with this. Y equals to log base b of x. By definition, this must mean that this number raised to that power must be equal to this, right? That's the definition. So that must mean that b raised to the y power must be equal to the x. Okay. All right, so now this we can take a derivative of. So let's take the derivative with respect to x of b to the y power, and then the derivative with respect to x of x. The right-hand side is super easy. Well, that's just going to be 1. The left-hand side, well, remember that this is the derivative with respect to x, and we don't have an x here, we have a y. So we got to use our implicit differentiation. We're going to take the derivative of this, with respect to y, and the derivative of b to the y power is equal to b to the y power times ln of b. So this is going to be b to the power of y times ln of b times, and now I got to take the derivative of the y. Let me make some room here. Times, and now it's the derivative with respect to x of the y, and on the right hand side there was that 1 from there. Okay, so this is good old chain rule. And now this, well, that's exactly what I'm looking for. The derivative with respect to x of the y. So this is just our y prime, just to kind of get a different notation. Or you can also write it as dy dx, right? So like this, or a lot of people go to the other notation style of saying that this is dy dx, like that. Same thing. This, or the y prime. I prefer the y prime. Y prime. Remember, this is just some constant. So this is going to be b to the y power times ln of b times y prime. Okay, so let's bring this up here. So let's see, that's going to be b to the y power times ln of b y prime equals to 1. So let's divide both sides by this, and we get that y prime is equal to 1 divided by b to the y power times ln of b. But b to the y power, well, that was x. From right here. So I'm just going to replace that and say that y prime is equal to 1 over x ln of b. Okay, and this is the answer. Or we can separate it. Sometimes we see it separated like this. Y prime equals to 1 over x times 1 over ln of b. Good. And so let's bring it all together. This is the boxed up version that your author provides for you. Okay, so this is the boxed up version that your author provides for you. The derivative with respect to x of log base b of x is equal to 1 over x ln of b. Okay, so now we have another derivative that we get to use. Let's apply it in some examples. Given y equals to log base 7 of x, find y prime. No problem. Just following our little rule, we know that this is equal to 1 over x times 1 over ln of 7. Okay, given y equals to ln of x, find y prime. Okay, well, remember that ln of x is the same thing as just our standard log base e of x notation. It's just a log function base e. We just happen to call it ln. So let's find that derivative. Y equals to ln of x is the same thing as log base e of x. Same thing. Okay, and so now we can find our derivative. Y prime is equal to 1 over x times 1 over ln of e, which becomes a 1. So y prime equals to 1 over x times 1 over 1. And so y prime equals to 1 over x. Okay, So now we have another derivative, very commonly used derivative. Given ln of x, the derivative with respect to x of ln of x is equal to 1 over x. This is the boxed up version your author gives you. Okay, so this is the boxed up version that your author provides for you. The derivative with respect to x of ln of x equals to 1 over x. Very, very common derivative. Yet another derivative in our tool that we get to use. Okay, so now let's apply this rule with another example. Okay, given that y equals to ln of 1 minus x to the second power, find y prime. Okay, so to start off with, y prime is going to be equal to the derivative with respect to x of ln of 1 minus x squared. So if we use our chain rule and we pretend this is a single variable like u, I'm going to let u equal to 1 minus x squared, then y prime is equal to the derivative with respect to u of ln of u times the derivative with respect to x of the u. Good. Okay, so then this part here is, so this is just going to be equal to 1 over u times this, which is the derivative with respect to x of the u, which is 1 minus x squared. Good. And the derivative with respect to x on this guy is just going to be minus 2x. So this is going to be equal to 1 over u, which is going to be 1 minus x squared, times, and this one is going to be equal to negative 2x to the power of 1. And so we've arrived at our final answer. Y prime, the derivative, is going to be equal to this big fraction where we have a negative 2x in the numerator and a 1 minus x squared in the denominator. Okay, so based on this, we can establish yet another rule involving logs and the chain rule. So here is what your author provides for you. So here's the rule that your author provides for the derivative with respect to x of ln of u equals to 1 over u times du dx. Right, that's exactly what we did here. All right, let's apply it again. Okay, find the derivative with respect to x of ln of cosine squared x. Okay, so this initially is going to be equal to the following. So let's do our u substitution. Let's let u equal to cosine squared x. So this will be equal to the derivative with respect to u of ln of u times the derivative with respect to x of the u. So this is going to be equal to 1 over cosine squared x. Takes care of this derivative, 1 over u, where u is this, times the derivative with respect to x of cosine squared x. Good. And again, we're going to have to do a substitution here. So let's let this is equal to 1 over cosine squared x times, and then remember that this is the same thing as cosine of x raised to the power of 2, right? We're squaring the whole cosine. This is, not to be confused with cosine of x squared. So this is the derivative with respect to x of this entire thing. Okay, so we're going to do a little substitution. I've already used u, so let's just mix it up and use w. How about if we let w equal to cosine of x? If we let w equal to cosine of x, then this derivative, the original derivative, is going to be equal to 1 over cosine squared x times, and now it's going to be the derivative with respect to w of w squared times the derivative with respect to x of the w, right? Our good old chain rule once again. And so this becomes 1 over cosine squared x times 2 times w to the first power times the derivative with respect to x of the w, which was cosine of x. Good. So now all we have to do is replace that w, 1 over cosine squared x times 2 times the w, where the w is cosine of x, times the derivative of cosine, which is equal to negative sine. Good? All right, so now we're set to write down our final answer. If we have the derivative, if we're asked to find the derivative with respect to x of ln of cosine squared x, the answer is going to be this, and let's put it all up in the numerator. So these are up in the numerator. It'll be negative 2 cosine x sine x. We can also use the double angle formula here to simplify that, but if you don't see it, don't worry about it. And then the denominator is going to have this cosine squared x. Good. So that's the derivative. Say y equals to 1 over ln of x. Find y prime. Okay, so first thing I would do is rewrite this so that it equals to ln of x, and then the whole thing is raised to the power of negative 1. Okay, so now we can use our chain rule. Again, we're going to let u equal to ln of x. And so that means that our derivative, y prime, is going to be equal to ddu of ln, of u to the negative 1 power times the derivative with respect to x of the u. So this will be y prime equals to, now we bring that negative 1 out in front, u to the negative 1 minus 1 is going to be to the power of negative 2, times the derivative with respect to x of the u, which is ln x. Okay, so y prime is equal to negative 1 over u to the negative 2 power times 1 over x. Almost there. So let's come back over here. So that means that y prime is equal to, oops, I made a mistake here. This is, let's come back over here. This is negative 1 times u to the negative 2 power. So then this becomes negative 1 over u to the positive 2 power times 1 over x. And then the u is actually ln x, so y prime becomes negative 1 over x times ln x squared. There we go. There's our answer. Say function notation, let's say f of x equals to log base 3 of 2 plus e to the x power. Okay, find f prime of x. Okay, so f prime of x is equal to, again, I'm going to do a substitution here, so we can use our chain rule. Let's let u equal to the 2 plus e to the x. So I'll have that this is the derivative with respect to u of log base 3 of u times the derivative with respect to x of the u, which gives me that this is going to be equal to 1 over u times 1 over ln of 3 times the derivative with respect to x of the u, which is 2 plus e to the x. And now the u, well, we have to resubstitute that in. This is going to be 1 over, the u is 2 plus e to the x times 1 over ln of 3 times the derivative of this function. The derivative of 2 is 0, and the derivative of e to the x is e to the x. So we've arrived at our answer here. So f prime of x is equal to e to the x, and then ln of 3, and then 2 plus e to the x. Okay, another example. Given y equals to ln of, and then we have this giant fraction where we have 2 minus x in the numerator, and then an x plus 4 in the denominator. let's find this derivative. Okay, so find y prime. Okay, so again, we're going to do a little u substitution. We're going to let u equal to that whole thing, 2 minus x all over x plus 4. And then we have that y prime is going to be equal to d du of ln of u times the derivative with respect to x of the u. So this one's going to be easy. The derivative of this part is just going to be 1 over u times the derivative with respect to x of the u, which is 2 minus x all over x plus 4. Okay, now for this guy, we're going to use our quotient rule. So this means that y prime is equal to 1 over, and then there's a little fraction down here where we have a 2 minus x and an x plus 4. So that's just substituting the u from there. Times, okay, so here we're going to use our quotient rule. Low d high minus high d low, right? Remember that little tick mark there? I should probably maybe put it in a different color. This little tick mark here is another way of saying that we want the derivative. The derivative of this guy, the derivative of this guy, all over the denominator squared, all over x plus 4 squared. Low d high minus high d low over the denominator squared we go. Okay, so now the derivative of this is super easy. The derivative of this is just going to be negative 1. The derivative of 2 is 0. The derivative of minus x is going to be negative 1, minus 1. And the derivative of this is just going to be positive 1. So we can simplify things. Okay, so then this becomes y prime equals 2. Now here we want to multiply the numerator times the reciprocal of the denominator. So we end up with 1 times x plus 4 divided by 2 minus x times, and then in this we end up with a giant fraction. We have the x plus 4 squared in the denominator, and then we end up with a minus 1 times an x plus 4 minus, and then we end up with a 2 minus x. Okay, we're going to distribute, combine, cancel. So this term here, this whole term, cancels with one of these. And then when I distribute, I'll end up with a minus x minus 4 minus 2 plus x when I distribute this minus. And so let's copy that over here. So we get y prime equals to a fraction where now the denominator is just going to be 2 minus x, and this just becomes 1. This got canceled. Times another fraction where the denominator now only has one copy of the x plus 4 since one of them was reduced. And in the numerator, we end up with a minus x minus 4 minus 2 plus x. So this minus x, this plus x cancel, and we end up with a minus 6. So we're almost there. I can bring them all together into one big happy fraction and just have a minus 6 in the numerator. And in the denominator, we end up with a 2 minus x times an x plus a 4. Okay, there we go. There's our derivative. Okay, let's think about f of x equals to ln of, and just to be really clear, this is the absolute value of x. Okay, this function can be separated into two different sort of a piecewise function. So this means that f of x is defined to be ln of x if x is strictly greater than 0. Right? So in other words, if the input happens to be positive, a positive number, then don't do anything, right? There's no more absolute values. Okay, on the other hand, if the input is negative, x is less than 0. If you're going to input a negative x in here, that means x is negative. Well, we know from our domain of log functions, we're not allowed to plug in a negative in here. The absolute value is that's when it kicks in, and so there's this extra term of -1. Right? That's what the absolute value would have done. It would have made any negative into a positive by multiplying it by -1. So the description of ln is an absolute value can be broken up into these two things, right? These are the instructions for absolute values. If the input is positive, leave it alone. It's the same thing. It's just x. If the input is negative, multiply it by -1 to make it positive. Good. Okay, so if f of x equals to ln of x, that's the same thing as saying f of x equals to these two functions. So we can treat them separately. So now when I want to find the derivative of f of x, which is the same thing as the derivative with respect to x of ln of absolute value of x, right? The derivative with respect to x of ln of x. Okay, well, what I could do is take care of it on a piece-by-piece basis. I could say, well, let's find the derivative with respect to x of ln of x for this case when x is positive. And then separately think about, well, what is the derivative with respect to x of ln of negative x when x is a negative? Okay, so I'll put the conditions in a second. This one's super easy. The derivative with respect to x of ln of x, when we know x is positive, is just going to be equal to 1 over x. And this is if x is greater than 0. No problem. What about this one? Well, this is going to be very similar. It's going to be 1 over minus x times the derivative, right? This is technically a chain rule, right? We're going to let u equal to negative x. So it's ln of u. It's going to be 1 over negative x times the derivative with respect to x to this one, right? You know what? Let me write it in more detail over here, but I just want to kind of condense it. So the derivative with respect to x of ln of negative x, technically we're going to let u equal to negative x, right? And so we'll end up with the derivative with respect to x, the derivative with respect to u of ln of u times the derivative with respect to x of the u. So we know this is going to be 1 over u times the derivative with respect to x of negative x, and that's just going to be a -1. So u was going to be 1 over negative x times -1, and so the whole thing cancels to give you 1 over x. And that's what I was going to write here. So if we just, without letting the actual substitution of u, if we just assume that this is a single letter, its derivative is 1 over that letter, so 1 over negative x, times the derivative with respect to x of the u, which gives you an extra -1. And so the whole thing becomes 1 over x. And so if, this is for the case of if x is negative. Okay, and so the point here is to notice that in either case, we end up getting the same answer. Whether it's positive or negative, we end up getting that the derivative of ln of absolute value of x is equal to 1 over x. Right, so that's another one of our derivatives that we get to use. And here is how your author presented it to you. So the derivative with respect to x of ln of absolute value of x equals to 1 over x. This is, I don't think this is not a very dramatic revelation. We saw earlier that if the absolute values weren't there, so we saw earlier that if we had the derivative with respect to x of ln of x, no absolute values, that its derivative was 1 over x. The only thing this is really extending is that here, this is in the domain of ln. So over here, we were guaranteeing that x was a positive number. But now we're saying, well, x could also be a negative number, and we get the same derivative. Good. Okay, so now let's try this really hard function. So given that y equals to this crazy ugly thing, find its derivative. What we want to do is take advantage of all the awesome properties of logs. So to solve this one, what I want to do is apply ln to both sides, or this way, ln of y. So stick y into the argument of ln, and then this whole thing into the argument of ln of x to the 1/3 power, square root of x plus 1, 3 minus 2x to the power of 2. Now, it didn't have to be log base e to solve this. You could have done it with log base anything. Log base 10 is also very popular. But log base 10 and log base e are both very popular because most calculators, most standard simple calculators, have these two functions built into the calculator, so you have a button for it. Whereas, another random base like log base 7 or log base 13 or something might not be a button that's kind of a standard button on your calculator. Some of the nicer calculators let you choose the base of your log, so then in that case it truly doesn't matter what you use, but most basic calculators don't let you change the base of your log. That and just sort of custom, it's kind of customary to work with ln. It's just, I guess, traditional. But okay, let's move forward then. So now the reason we do this is because I can take advantage of properties of logs to break this ugly thing up into little pieces. So for starters, we know that if we're dividing a divided by b in the argument of a log, then that means that it's equal to ln of the numerator minus ln of the denominator. Good. Next, we know that if we're multiplying two terms in the argument of a log, so a times b inside the argument, that turns into the addition. So this would be ln of x to the 1/3 power plus ln of square root of x plus 1 minus, and we know that if we have an exponent, an exponential number inside the argument of the log, we can bring that exponent out in front. This becomes 2 ln of 3 minus 2x. And then we can also think of this as x plus 1 to the power of 1/2. So we can simplify this to be 1/3 ln of x plus 1/2 ln of the square, not the square root, got rid of the square root, ln of x plus 1 minus 2 ln of 3 minus 2x. Okay, so on the left-hand side is still ln y, and we still haven't taken a derivative. I just used the properties of logs to simplify the whole expression. Okay, but the point was to find that derivative, so now let's take the derivative with respect to x of everything. So now, the derivative with respect to x on the left-hand side, ln y, is equal to the derivative with respect to x of 1/3 ln of x plus the derivative with respect to x of 1/2 ln of x plus 1 minus the derivative with respect to x of 2 ln of 3 minus 2x. 3 minus 2x. Okay, so the derivative here, we're going to use our chain rule. This is going to be equal to 1 over y times the derivative with respect to x of the y, which is our y prime. Okay, that's what we're really after. Here, this is going to be equal to 1/3 times the derivative of ln x, which we know is equal to 1 over x. Another reason why we choose ln is because its derivative is really nice. Plus, and then this is going to be equal to 1/2 times, and then we're going to technically use a chain rule here, let u equal to x plus 1. So it'll be equal to 1 over x plus 1 times the derivative of the u, the derivative with respect to x of the x plus 1, which is just going to turn out to be 1. So it doesn't really change anything. Minus, and then here again we have a 2 times 1 over 3 minus 2x using the chain rule. Again, we're pretending this is a single letter, the derivative of that letter. So let's say w. So ln of w, its derivative is 1 over w, times the derivative with respect to x of the 3 minus 2x, which turns out to be just minus 2. Minus 2. Minus minus is going to be plus 4 in the numerator. So let's zoom out a little bit and bring this up here. So we have that 1 over y times, and I'm going to write it as y prime, equals, so 1 over y times y prime equals to, this is going to be 1 over 3x plus 1 over 2 times x plus 1. Remember, this is a 1 there, okay, and then we get a minus minus plus 4. So plus 4 divided by the 3 minus 2x. 3 minus 2x, okay, so that looks like I copied it right. Let's zoom up here now. So we're almost there, except I wanted to solve for y prime, not y prime divided by y. So all I have to do is multiply both sides by y, and I'm there. So y prime is going to be equal to y times this whole thing. 1 over 3x plus 1 over 2x plus 2 plus 4 over 3 minus 2x. And then all we have to do is substitute the value of y, what we started with. So y prime is equal to, and then remember y was this ugly mess over here. This original nasty mess over here, that's y. So it becomes x to the power of 1/3 times the square root of x plus 1 divided by 3 minus 2x squared times, and then that. So let's copy that. This becomes times 1 over 3x plus 1 over 2x plus 2 plus 4 over 3 minus 2x. There. So that's our final answer. That's our derivative. See if I can get it all in one screenshot. Okay, one more example. So y equals to sine of x raised to the power of cosine of x is given. Find y prime. Okay, again, we're going to take advantage of our properties of logs to be able to do this. So we're going to say, let's look at ln of y equals to ln of sine x raised to the power of cosine x, where this is an exponent. And our properties of logs, let us bring that in front. So we get cosine of x times ln of sine of x equals to ln of y. Good. So now we can take the derivative with respect to x. This is derivative with respect to x of ln of y is now equal to the derivative with respect to x of this product. So we have the product rule. So derivative of cosine, so we need cosine of x, and then we're going to take its derivative, times, leave the second one alone, times ln of sine of x plus, now we're going to leave the cosine alone, cosine of x, leave that alone, and we need to take the derivative with respect to x of the ln of sine of x. So take the derivative of this one. Okay. On the left-hand side, we've seen this several times now. This is just going to be equal to 1 over y times y prime. That's the derivative of this using the chain rule. And the derivative of cosine of x is equal to negative sine x, so that's no problem, times ln of sine of x, no problem there. Cosine of x times, and now using our u substitution, like u equal to sine of x, that's just going to be equal to 1 over sine of x, times the derivative of sine of x, ddx of sine of x. So that's using their chain rule. We get 1 over y times y prime equals this mess, and the derivative of sine of x is equal to cosine of x. So we end up with y prime equals to y times, and this is going to be minus sine x times ln of sine x plus, and the derivative of sine is going to be cosine, so I'll end up with cosine squared, the derivative of sine is going to be cosine of x. So I'll end up with cosine squared over sine. Cosine squared x over sine of x. Okay, and so now all we have to do is replace that y with our original value, and then that's our derivative. So y prime is going to be equal to sine of x to the power of cosine of x times negative sine x times ln of sine of x plus cosine squared x divided by sine of x. I don't believe that there's much value in trying to simplify this any further. We end up with a sine squared over sine. Yeah, I think that that's about as good as it gets, so I would just stop there. Okay, try and put everything in one box. Okay. Okay, so finally, we want to bring all the skills we've learned so far to be able to come up with a limit description of E. We've been using E for a while, and in a prior video, I kind of introduced a little bit what it is and gave you an idea, but now we're going to do a more formal presentation of how we define E, how we come to establish the value of E in terms of a limit definition. Okay, now let's consider the following. Let's say f of x is equal to ln of x. Its derivative, we know by now, very easy. The derivative is equal to 1 over x. So if we wanted to evaluate this at 1, the derivative of this function at 1 is equal to 1 over 1, or just 1. F prime of 1 equals to 1. Okay, but now let's think about the derivative in terms of the original definition of a derivative. So given that f of x is ln of x, its derivative, f prime of x, is equal to the limit, remember back to the limit definition, the limit as h goes to 0 of f of x plus h minus f of x all over h. All over h. Okay, so now if the function is ln of x, then that means the derivative with respect to x is going to be the limit as h goes to 0 of ln of x plus h minus ln of x, the whole thing divided by h. And now in particular, so this is more of a general derivative, but I'm interested in 1. So then by the definition, f prime at 1 is going to be equal to the limit as h approaches to 0 of ln of 1 plus h minus ln of 1, all of that divided by h. And we know that the derivative of 1 is always equal to 0. So this is ln of 1 is 0, so that disappears. So I get that the derivative, f prime of 1, is going to be equal to the limit as h approaches to 0 of these two, the division of these two. So I'm just going to move it in front and say it's 1 over h times ln of 1 plus h. Good. Okay, well, now we come to algebra's favorite trick. Let's change all functions to x. I don't know why. It's just customary. Algebra loves x. So this is a function in h, right? The limit as h goes to 0 of this thing. And, we're trying to express an idea. There's nothing special about the letter h. So I could say the exact same thing as the limit of w going to 0 of 1 over w times ln of 1 plus w, for example. All I did is change every h with a w, same thing. So likewise, instead of an h, I can go to algebra's favorite letter. Limit as x goes to 0 of 1 over x times 1 plus x. Like this. Good, good, good. Okay, so f prime of 1 equals to this. And now, okay, well, we know our properties of limits. If we have a numerical factor out in front, we can raise it to the exponent. So this is the same thing as f prime of 1 is now equal to the limit as x approaches to 0 of ln of, and then inside the argument of the ln function, we have 1 plus x raised to the power of 1 over x, right? All of that is inside the ln argument, right? Moving this in front, moving this term out to the exponent. Okay, but we already knew that the derivative evaluated at 1 was equal to 1. So bringing those two things together, so bringing this guy along with this guy together, then we can conclude that f prime of 1, which was equal to 1, is also equal to the limit as 8x goes to 0 of 1 over x ln of 1 plus x raised to the power of 1 over x. Okay, so we're just going to focus on this part here. So that's one thing we know. Okay, now I'm going to remind you of something way back from limits. So way back when we were working with limits, we had this property. So way back in chapter 2, we had this theorem. If f is continuous at b and the limit as x approaches to a of g of x equals to b, then the limit as x approaches to a of f of g of x equals to f of b, right? So then that can be condensed into this statement here. So if we have a composition of functions and they're trying to find the limit as x approaches to a to this composition of functions, then what you could do is evaluate the outer function at the limit of the inner function. For example, just a quick little example, the limit as x approaches to the number 3 of the equation 5 minus x. Super easy. We know that this limit, well, it's just a polynomial. We can just plug it in. We know this limit equals to 2. Good. Okay, so if we had 4 to the power of 5 minus x, and we're trying to find the limit as x approaches to 3, right? So what we have here is an outer function and an inner function. So we can think of this as composition of functions where we let f of x equal to 4 to the x power, and we have g of x equal to 5 minus x. And so this is now, according to this, is equal to the 4 to the power of the limit as x approaches to 3 of 5 minus x, which then gives you 4 to the power of 5 minus 3, which is just going to be equal to 4 to the power of 2, which gives you 16. Okay, so if we have a composition of functions, there's an outer function, an inner function. then we can evaluate the outer function at the result of the limit of the inner function, as long as f is continuous at that point. So this all worked out because the function 4 to the x is continuous at x equals to 2. So note, 4 to the x is continuous at x equals to 2. So that's why it worked out. If the result of this limit is something which is not a value where 4 to the x is continuous, then this wouldn't work. Okay, just an oldie but goodie to remind you of what I'm about to do now. So let's put that in a separate thing. Okay, so I'm going to focus right in here, and this is what we want to do. I want to figure out what is e to the power of 1 going to be. Okay, so now that we're armed with all of that, this is what we really want to do. We want to figure out the following. E is equal to e to the first power. And 1, well, we already established that 1 is equal to that really complicated, let's put it below. We've already established that 1 is equal to that limit, right? So e is equal to the limit as x approaches to 0 of ln of parentheses 1 plus x to the power of 1 over x. Right? I'm just saying the 1 here is the same thing as this complicated thing. We established that up here. It's right here in our box. 1 equals this complicated limit. 1 over x times ln. Oh man, I made a mistake. So this 1 over x is not here, right? It's being redundant. I'm being redundant here because this is, this shouldn't be here. Because I've already moved it up to the numerator. So from here we saw that it was moved up into the exponent. So really it should have been this. Sorry. And so that's what this is here. Okay, and now using our properties of logs, we can see that e to the power of x is the outside function. You can think of e to the f of x as equal to e to the x power as the outside function. And then this, whatever this is the inside function, which we know is equal to 1. And we know that e to the x power is continuous at x equals 1. Good. So for that reason, we're allowed to do the following. We're allowed to swap this out in front and say that it's equal to the limit as x approaches to 0 is equal to the limit as x approaches to 0 of e to the power of ln of parentheses 1 plus x to the power of 1 over x. Right? Usually we start like this. Usually back in chapter 2 we said let's find this limit, and then we would say, well, this is an outside function, e to the x, and so we can swap it and find the limit of the inside function, which would be this, and then evaluate the outside function at the inside function. That's what this lets us do. Okay, and now this can be reduced because e to the x and ln of x are inverse functions, so they undo each other. And so the end result is going to be that this is equal to the limit as x goes to 0 of just the 1 plus x to the power of 1 over x. So if we marry all those things together, we end up with the following. E is equal to, we end up with saying that e is equal to that. The limit as x approaches to 0 of 1 plus x to the power of 1 over x. That was really the whole point of this. Okay, this is what your author presents to you. So this is what the author provides for you. E equals to the limit as x approaches to 0 of 1 plus x to the power of 1 over x. Okay, so what we've established here is a limit definition of e. We've seen it before, but now we can see the roots of it, where it came from. Okay, so this should be more than enough to do the homework. So please try your homework out and come to my office hours if you have any questions.